Hi guys, this part of the lecture that has the loudspeaker pictures is the asynchronous part of the lecture. That means that you can go over it before I start the official synchronous class at 7 p.m. on November 3rd, or afterwards, meaning after the class at some point. What we are going to cover is this idea of the relationship between the microscopic and macroscopic. This is important because the main issue that we will be covering in a chapter about fluids will be about pressure. And pressure can be explained using microscopic notions, which include, for example, momentum, forces, etc., and macroscopic, which will be pressure.
Look at this hot air balloon, for example. Obviously, it is in Earth's atmosphere. As a result, there is pressure in the outside region. But inside the balloon, there must be pressure as well, or else it would have collapsed. What keeps that balloon floating? Why is it that the balloon actually ends up going upwards with hot air inside it? Inside every enclosement there are molecules, and I have a picture here of a box with molecules in it. Every molecule moves. Since those molecules have both mass and velocity, they will slam into walls and apply pressure on those walls. That internal pressure by the hot air must as well be at least as large as the pressure in the outside. In order to see that this is really so, let's be a little bit more specific. Specifically, let's look at one molecule moving specifically along one direction. Let's look at this specific molecule. I'm assuming at first that this is like really not a molecule, but a ball that bounces with 100% efficiency, meaning that it goes at 10 meters per second, slams into a wall, bounces back at 10 meters per second. Maybe this wall is somewhere out in space so that gravity doesn't do any effect to it. So it just goes back and forth at 10 meters per second, and each time it hits the wall, it gives the wall a little bit of a push. Looking at the units that we learned, I want to find out how much of a push. So not just the push, but also the pressure will be of interest. There is a reason for that, as you will see fairly soon. Once we generalize from one molecule to a whole lot of molecules, we may be able to explain the pressure in the room, in a balloon, etc. Bear with me for a moment. I know this looks a little scary, but the main idea here is for you to see orders of magnitude here. Here is that ball bouncing back and forth from the wall. And when you look at the numbers, you'll find out that with this ball at this speed, crossing the 3x3x3 room, a force on the wall would be 33 Newton. That's about the weight of a small cat. You can then divide force by area and you get pressure, which is very, very tiny pressure by that large, massive, quick ball. Compare that with the actual atmosphere, one atmosphere you have in a room, which is 100,000 Pascal. And you'll find out that it's not that much, meaning that all those unseen particles in the room make a huge contribution. They must be fast, not just small, and there must be lots of them. And that is correct. The other thing you can get just from this analysis is that you could find out that pressure is proportional to this mv square over volume. You may recall that energy of something getting near the sun and away from the sun, near the sun, away from the sun, kinetic energy, is half mass velocity square. Basically, that is the kinetic energy of a particle. This will help us out in the next slide. If you go to any chemistry book, you'll find something called PV equals nRT. Pressure is the number of moles times a number times the temperature divided by the volume. That temperature is actually the temperature above absolute zero. But now you have a recollection here that in the previous slide we found that pressure is that half mv square over the volume. So except for that mole thing, we see temperature and kinetic energy being quite connected with one another. Indeed, the temperature times some number is the kinetic energy of a particle. Now think about it. This is quite a discovery. First of all, what temperature do we have in which all the particles stop? That's when the kinetic energy goes to zero. Well, that's gonna be the absolute zero temperature. It's involved kinetic energy that's zero. So when a particle slows down very much, it gets to zero. You can't slow below zero, that's why you don't get negative temperatures. Now let's look at the balloon question again. If you have fewer particles in the room, you have lower pressure, as the gauge shows in the top picture. In the second picture, the number of particles bigger, and therefore the pressure is larger. In the third picture, the number of particles is the same as in the first picture, but the pressure is still larger because the kinetic energy of the particles is doubled. When the kinetic energy is doubled, the pressure doubles. When the temperature doubles, the pressure doubles for the same amount of particles as in part 1. That is the reason for the balloon floating in the second slide. Hot air balloons are hot, and therefore to arrive at the same exact high pressure, we need fewer particles because each of them has more kinetic energy. You provide them with energy into the balloon in the form of heat, and each particle moves fast enough so that we don't need as many. Therefore, in the balloon we have fewer particles. The total mass of the balloon per volume is less than if it was cold, because when it was cold, for the same pressure you needed twice as many particles. Therefore, you kind of push out a lot of the particles, and the total mass inside the balloon is less. Things that are less dense float. Consider a helium balloon. That one is at the same temperature as the air. Why is this one floating? Well, notice that the kinetic energy of each particle is the same as the kinetic energy of other particles. Therefore, what can you tell about that particle? Here are a few facts about balloons. As you can see, helium balloons at the same temperature have enough kinetic energy to provide enough pressure inside the balloon, and as a result they don't need as many particles to support that pressure as the pressure from the outside by slower particles. Notice here that in answering this question you have to take into account the fact that particles are not influenced that much from gravity. As a matter of fact, the temperature that we have on Earth is sufficient for nitrogen and oxygen molecules to move at about 500 meters per second. That's about 1500 feet per second. That's fairly fast. And helium, as we said, is moving much faster. This is at the regular temperature that we have, which is at about, let's say, 50s or 60s. Hey, we wish we'd have that in Billings all the time, right? There's another question about Billings. Take into consideration the fact that we are at about almost a mile high in Billings. Here's a summary about air and pressure. It's basically the story of the microscopic atoms and molecules that have velocity and mass and apply many little forces on walls. And when you combine them all together, all trillions and trillions of them, trillions of them in each cubic meter, you get pressure that is atmospheric pressure. Without that pressure, if you would be, for example, in an evacuated room, you would boil off. So that pressure is important. That pressure is fairly large. That pressure is more significant than that of a big ball bouncing back and forth. There is a slight tiny imbalance that allows us to inflate a balloon. We inflate until we have just a tad of a force to hold the balloon itself from collapsing on itself, because the balloon is like a mini spring. So against that spring we apply pressure that's a little bit higher in the inside than from the outside. So from the outside you can think of the springiness of the balloon trying to push it in, and the air from the outside trying to push it in, and the slightly higher pressure from the inside, either by hot air or helium or other gases. That's what balancing the balloon from collapsing. Another word that's very useful is the word gradient. Gradient of pressure is what supports the atmosphere. We don't need a whole lot of pressure in the mountains to support against the column of air above, but we need way more pressure or more force per area to hold the atmosphere against the big column of air above it at sea level. Obviously, when we increase the air's density, or when we increase the air's temperature, in both cases we can increase the pressure. Look closely at the picture to the right. Each of the stripes, orange and purple, represents 1,000 kilograms of air. That's about 2,200 pounds of air in each 9 square feet. If you look carefully between 0 and 10, that's 0 and 10 kilometers, the first line corresponds to about 2 kilometers, that's just over a mile. That's where the first kilogram is. Okay? And so that means that if you're at a little over a mile, you will have 9/10 of the total weight of air above you, and hence 9/10 of the pressure. Well, in Billings, it's going to be a tad more than 9/10 because we're not quite a mile. But that also means that on your boiling water, there's 95% or so of the air that would be there if you were at sea level, and that doesn't even connect with the temperature. It doesn't matter. It could be within your house. Well, that would end up contributing to the fact that water in Billings does not boil at 212. It boils at a slightly less high temperature. As a result, you need to watch it when you cook. Make sure you cook things thoroughly. They may have not reached that 100 degrees Celsius or 212 Fahrenheit. Take a guess at this one. And be bold. That's the big hint. Be bold. Now think about it. We said that in that invisible room, what gave you 100,000 times more pressure than that of a 10 kilogram, of a few kilogram, 10 meters per second ball, is all those unseen air particles. So again, be bold. I told you that things that are less dense float. But there is a buoyant force whether you're dense or not dense. Everybody that took a bath knows that. And especially a fellow by the name of Archimedes. In about 200 BC, Archimedes lived in present-day Sicily in the town of Syracuse, and he was concerned about the density of the crown of the king. The king asked him, is the crown fake? Archimedes knew about densities. He knew that gold had higher density than silver. And he knew that a lot of forgers would use silver and plate it with gold. But how to find it? The crown was very intricate. He went and took a bath. The bath was completely full, so that with every inch that he went into the bath, some water overflew from the bath. And he was thinking, how much water did it take to flow out of the bath until I went in all the way? And his answer was, whatever it is that my volume was, that's how much water went out. And his brilliance was to show that the weight of the water that was overflowing is by how much weight he became lighter. Do it with the crown and you can find its weight, its volume, and therefore its density and whether it's forged or not. As a result, Archimedes jumped out of the bathtub, ran to his studio to run everything through his helpers, and forgot one little fact, which was that he forgot to put on his clothes. So he ran through the streets of Syracuse running and shouting, Eureka, Eureka, which meant, I found it, I found it.